Welcome to the deep dive. You've got this stack of sources, yeah, all about how AI and big data are, well, really shaking up investment management.
Mm-hmm.
It feels like there's just so much information now, almost an overload. And AI promises to help cut through that, find new value. But what's really going on under the hood?
Exactly. And that's what this deep dive is for. It's your shortcut, really, to getting properly informed. We're going to unpack these sources, pull out the key stuff, connect the dots between core AI ideas and how they're actually used in finance,
Okay.
and hopefully uncover some surprising things about how these intelligent agents learn and how all this computing power enables, well, pretty complex analysis.
Okay, great. Let's jump right in then, because our sources, they cover a lot of ground from the real basics of how machines learn by like trial and error, all the way to using massive computation for tricky things like risk assessment or building portfolios.
That's right. And, at the heart of that kind of learning through interaction is a concept called reinforcement learning, RL.
Ah, RL. Yeah, I hear that linked with teaching AI to play complex games or training robots.
Yeah.
It's basically learning by doing, isn't it?
That's a perfect way to put it. Yeah. RL is it's the problem of how an agent could be a trading algorithm, could be a robot arm, could just be software. Learns how to pick the best actions within some environment to achieve its goals.
Right.
And it learns through feedback, not necessarily being told the right move, but getting, rewards or maybe penalties for what it
Yeah.
does.
So the agent, it senses its environment, figures out its current state, it can take different actions, and then it gets some kind of reward signal back.
Hmm.
And its goal is to work out a strategy, a policy that tells it what action to take in any state to get the most reward over the long run.
Precisely. And maximizing the cumulative reward is the key thing. And often we discount future rewards. Getting a reward sooner is usually better than later, which, makes a lot of sense in finance.
Definitely does. So what are the really big challenges for an agent trying to learn this way?
Well, two really stand out, and they're super relevant for finance. First one is delayed reward. You might take an action now, but the actual payoff, the reward or penalty, it might not show up for ages.
Uh,
So the agent has to figure out, okay, which of my past actions actually led to this outcome I'm seeing now? That's called the temporal credit assignment problem.
like trying to pin down why a particular trade worked or didn't weeks or months later when everything's changed. That sounds tough.
It is. It's a really fundamental challenge. And the second big one is exploration versus exploitation.
Okay.
So to find the absolute best strategy, the agent needs to explore, it needs to try out new actions, things it hasn't done before, paths it doesn't know about.
Right.
But at the same time, to maximize the reward it's getting right now, it needs to exploit, stick with the actions it already knows are pretty good. It's this constant balancing act.
That sounds exactly like a portfolio manager deciding, do I stick with my tried and tested assets or do I explore this new, maybe risky market that could have a huge payoff?
Perfect analogy, yeah. And tackling these challenges is what makes RL so interesting and potentially powerful.
Okay, so these sources mention a specific way to handle this, an algorithm called Q-learning. How does that fit into the picture?
Right. Q learning. It's a really clever and widely used RL algorithm. It takes a slightly indirect route. Instead of learning the policy, the strategy directly, it learns an evaluation function. It learns something called QSA.
QSA. And what does that represent? What's the Q?
So you can think of QA as the estimated quality or the total future value of taking a specific action A when you're in a particular state as.
Okay.
More formally, it's the maximum discounted cumulative reward the agent expects to get if it starts in state as, takes action A first, and then it follows the optimal strategy forever after that. So it bundles up the immediate reward plus the discounted value of the best possible future path.
Got it. So it's not just the immediate kickback, but the whole chain of future rewards that action might lead to.
Exactly. And here's the really neat part about Q learning. If the agent could somehow learn the true Q value for every single state action pair,
Yeah.
then finding the best action in any state as becomes dead simple. You just look at all the possible actions A you can take from as, and you pick the one with the biggest Q as value. That's it.
Okay.
And crucially, the agent can learn these Q values without needing a perfect map of the environment beforehand. It doesn't need to know exactly how likely it is to transition between states or what the reward will be for every action. It learns just by trying things out, observing, and updating its estimates.
That sounds incredibly useful for something like financial markets, where you definitely don't have a perfect map of the future.
Huh.
So how does it actually learn these Q values? How does the update work?
It does it iteratively, step by step. So imagine the agent is in state as, it decides to take action as, it gets an immediate reward R, and it ends up in a new state. Let's call it prime. It then updates its previous estimate for Q. The core idea is it adjusts its estimate based on the reward it just got, plus the discounted value of the best possible action it could take from the new state. It uses its current best guess about the future from the new state to improve its guess about the value of the step it just took.
So it's kind of using its future expectations to refine its past evaluations, letting the value flow backwards.
Precisely that, yeah. The simple grid world example in the source material shows this really well. You see an agent exploring this little grid, right? When it finally hits the goal state with a big reward, say 100, in subsequent training runs, that reward value starts to trickle backward. The state right before the goal gets a Q value derived from that 100, like 0 immediate reward plus 0.9 times 100, maybe. Then the state before that gets a value derived from the state that's now worth 90, and so on. The value propagates.
That makes intuitive sense. And the sources say that for simple cases, like using a lookup table, Q learning is actually guaranteed to find the optimal Q values if you explore enough.
Yes, mathematically, under certain conditions, mainly, that you can represent all states and actions in a table, and you visit every state action pair enough times. But this brings us right back to that exploration challenge.
Right.
If the agent only ever picks the action that currently looks best, that's called a greedy strategy. It might get stuck in a rut. It might miss finding an even better path it just hasn't stumbled upon yet.
So you can't just be purely greedy, always exploiting.
Generally not, no. In practice, agents use strategies that miss it up. They might make actions with higher key values more probable, but still give a small chance to trying out other, less promising actions, especially early on when they're still learning the ropes.
Okay, so learning by doing, propagating value, balancing exploring and exploiting. But these lookup tables, they just won't cut it for real-world finance complexity, right? The number of possible states in the market is practically infinite. How do we scale this up?
Exactly. And that leads us straight into the need for function approximation. When your state space is huge, or maybe even continuous, think about all the possible combinations of stock prices, interest rates, new sentiment scores, economic data points.
Yeah, endless.
You just physically cannot store a separate Q value for every single one in a table. It's impossible.
You need something smarter, something that can generalize from the situations it has seen to new ones it hasn't encountered before.
Precisely. And that's where things like neural networks become really powerful. Instead of a massive table, you train a neural network to approximate the Q function.
Oh, okay.
The network takes the state, and maybe the action, as input, and it outputs an estimated Q value. You use the same core Q-learning update ideas, but now you're using them to tweak the connections, the weights, inside the neural network so that its output gets closer and closer to the target value calculated from the reward and its own future estimates.
So the network isn't just memorizing values, it's learning the underlying pattern of what makes an action good in different kinds of states. That's how you get systems like TD Jammin playing backgammon, or robots learning complex movements.
Exactly that. It allows Q learning and RL in general to tackle much, much bigger problems. But it's important to add a little caveat here, which the sources point out.
Yeah.
While using function approximators like neural networks is incredibly powerful for scaling up those nice mathematical guarantees about converging to the absolute optimal Q values that you get with simple tables, well, they don't always hold up perfectly when you use complex approximators. Training can be trickier, potentially less stable, might need more careful setup.
Right, more art than pure science sometimes. Applying these complex models, training them on the sheer volume and variety of data in modern finance, that must demand just incredible amounts of computational power.
Oh, absolutely. This is where accelerated computing becomes not just helpful, but essential. You know, AI and big data in finance, it's not just theoretical anymore. It's central to strategy finding alpha, managing complex risks, making operations more efficient. But the bottleneck is often processing the sheer scale of data market feeds, news, alternative data like satellite images, and doing it fast enough to be useful.
And standard computer processors, CPUs, they kind of hit a wall with that kind of parallel workload.
For many of these tasks, yes. They're great for sequential things, but training a huge neural network or running millions of simulations involves doing vast numbers of similar calculations all at once. That's where GPUs, graphics processing units, have totally changed the game.
Right. Originally for gaming graphics, but perfect for AI number crunching.
Exactly. They have thousands of cores designed for parallel processing. So for AI training, simulations, massive data manipulation, they can be orders of magnitude faster than CPUs. This means investment firms can build much more sophisticated models. They can analyze vastly larger data sets. They can iterate on ideas much, much faster, fail fast, fail forward, and get timely insights.
So it accelerates the whole research and deployment pipeline.
It really does. The sources mention benchmarks like MLPerf and Stack showing huge speedups for typical financial tasks. And it's not just training AI models like, say, using PyTorch or TensorFlow. It's accelerating the whole workflow.
Like what else?
Things like loading and cleaning the data itself. There are libraries like Rapids and cuDF specifically for doing data science tasks on GPUs. Then there's running the models once they're trained, inference, doing complex simulations like Monte Carlo for risk, pricing derivatives, backtesting strategies rigorously. Even the computation needed to explain what the AI model is doing, using techniques like SHAP, can be massively sped up by GPUs.
Okay, that's a broad impact. Let's make this more concrete. Let's look at some of the specific use cases from our sources where this accelerated AI is really making a difference. First one, ESG and risk analysis using NLP and document intelligence.
All right, this is a classic unstructured data challenge. Firms are drowning in text news feeds, company reports, social media, regulatory filings. They need to sift through all of it to understand ESG factors, environmental, social, governance.
Yeah.
But also to monitor for risks like negative news events about a company, or maybe just ensuring compliance with regulations.
And trying to read all that manually is just, forget it.
It's completely impossible at the speed and scale needed today. So AI, particularly natural language processing, NLP, is the key. NLP tools can automatically do things like figure out the sentiment, is this news positive or negative? Identify which companies or people are mentioned, pull out specific facts or numbers hidden inside long, dense reports, or even understand the meaning well enough to classify information according to different ESG reporting standards.
So it helps analysts quickly flag potential issues or extract key data points from mountains of text.
Exactly. The sources give the example of trying to detect greenwashing, when companies might exaggerate their environmental credentials. NLP can help by comparing what a company says in its official reports versus what's being reported in the news or other sources. It acts as a sort of automated watchdog.
That makes sense.
And accelerated computing is vital here because training powerful NLP models, especially the huge large language models, LLMs, that are state-of-the-art now, requires immense computation. Processing millions of documents also needs that parallel power. GPUs make it practical to build and deploy these kinds of systems.
Okay, moving from text to pictures, essentially. Another really interesting area is using Earth observation, EO data, and spatial finance. What's going on there?
Yeah, EO data is basically information from satellites, drones, other sensors, giving us a view of the physical world. It's objective, often very timely, and can provide insights into things like physical assets, supply chains, environmental changes.
Right.
But the data itself is complex. We're talking huge images, often sequences of images over time, covering large areas.
And spatial finance, that's about weaving this geographical data into financial analysis.
That's the idea. Integrating geospatial data and analysis directly into financial workflows. It's particularly relevant for understanding and managing climate-related and environmental risks. Think deforestation impacting agriculture, water scarcity affecting industry, or the physical risks to properties from floods or wildfires. The sources say this is a really fast-growing field.
So how does AI help analysts make sense of all these satellite images and sensor data?
You need specialized AI techniques, often falling under the umbrella of GeoAI or using advanced computer vision. These models can be trained to automatically identify specific things in the imagery, like pinpointing the location of factories or solar farms, measuring the extent of deforestation or crop health, maybe even detecting signs of pollution or monitoring construction activity.
So it's like having eyes in the sky that can verify company claims or spot trends early.
Pretty much, you could use it to monitor shipping activity at ports for insights into global trade, or track crop yields for commodity trading, or, as you said, assess the flood risk for specific buildings in an insurance portfolio based on terrain data and weather patterns.
Fascinating. And again, the scale of this data must mean acceleration is key.
Absolutely indispensable. Processing these massive image files, running complex data pipelines to prepare the data, training and running sophisticated computer vision models, it all requires huge amounts of parallel computation.
Right.
The sources also mention things like physics-informed AI models for climate simulation or using platforms like Omniverse for creating digital twins of physical assets. These are computationally very heavy tasks where GPUs provide the necessary horsepower. It just makes analysis possible at a scale and resolution that wasn't feasible before.
Okay, so we've covered text, we've covered images. What about good old-fashioned financial market data? The sources also talk about using AI and simulation for building diversified portfolios.
Yeah, this is about addressing some limitations of traditional approaches. For example, modern portfolio theory, MPT, while foundational, can sometimes suffer from issues like strategies looking great in backtests on historical data, but then failing spectacularly when deployed
Ah,
live.
yes, backtest overfitting.
Exactly. Or relying too heavily on estimates of how assets move together, correlations, which can be really unstable and noisy, especially during market stress.
So how are AI and simulation helping here?
One really interesting approach is generating realistic synthetic market data. Instead of just relying on the one path history actually took, which might not represent future possibilities well,
Wow.
you can use AI techniques like generative adversarial networks, GNNs, or other simulation methods to create thousands, even millions of plausible alternative market histories, scenarios that are statistically similar to the real world but have never actually happened.
Wow. Okay. So you can basically create countless what-if worlds to really put your strategies through their paces, beyond just what happened in the past.
Exactly. It allows for much more robust stress testing and validation. Then, another layer is using machine learning on top of this. You can train an ML model to look at the characteristics of a particular market scenario, maybe generated synthetically, maybe real-time data, and predict which type of portfolio construction method is likely to work best in that specific environment.
So not just assuming one method works all the time.
Right. Maybe traditional MPT is good sometimes, but maybe in other conditions a different approach, like hierarchical risk parity, HRP, might be better.
HRP, what's the idea behind that?
HRP is a newer technique that uses ideas from graph theory. It tries to build portfolios by first clustering assets based on how similar their behavior is, creating a kind of hierarchy, and then allocating risk across these clusters. One key advantage is that it avoids needing to invert the covariance matrix, which can be mathematically unstable if correlations are noisy or assets are highly similar.
Huh?
But, as the sources note, HRP isn't a magic bullet either. It doesn't always beat MPT. Its relative performance can depend heavily on the market regime.
So the AI helps choose the right tool for the current market conditions. And I'm guessing generating millions of synthetic scenarios and training these predictive models, that takes a lot of compute.
A massive amount. Generating high-fidelity synthetic data, especially capturing complex correlations realistically, is very computationally intensive. Training the ML models is demanding too. And then there's the crucial step of explaining why the AI recommended a particular approach.
Right, the black box problem.
Exactly. Portfolio managers need to understand the reasoning. Calculating explanation scores like SH8 p-values, especially for complex models like tree ensembles, can be surprisingly computationally expensive. GPUs provide huge speedups here, making the whole cycle of simulation, prediction, explanation, and validation much faster and more practical.
Okay, so we've seen these powerful data-hungry AI methods, often accelerated by GPUs, being applied across text, images, market data. But the sources also highlight a completely different philosophy, don't they? Symbolic AI.
They do, yes. Symbolic AI is a different branch of AI altogether. It's less focused on learning statistical patterns from vast amounts of raw data and more focused on representing knowledge explicitly, using symbols, rules, and logic that humans can understand.
So it's based on encoded knowledge rather than discovered patterns. Why is that relevant for investment, especially when everyone's talking about big data?
Well, it's particularly relevant in situations where maybe you don't have massive amounts of clean data for a specific problem. Or, perhaps more importantly, in areas where transparency, interpretability, and the ability to directly leverage deep human expertise are absolutely critical.
Like in fundamental investing.
Exactly. Think about fundamental stock picking or real estate investment. The decisions are high stakes, often based on complex, nuanced reasoning that combines data with judgment and experience. Investors need to understand why a system is recommending something. They need to be able to trace the logic and trust it. Symbolic AI allows you to take that human expertise, that reasoning process, and actually write it down as explicit rules the system can follow.
So you can audit the reasoning. That makes sense. This is brought to life in the case study of Samuel at APG Real Estate, right?
Yes, Samuel is a fantastic example. It's described as a composite AI system, meaning it likely combines different techniques, but its core is symbolic. It's designed to act as a kind of digital colleague for APG's real estate investment team.
A digital colleague.
I like that.
Huh?
Yeah. And its key selling point is that it provides advice that is transparent, systematic, and really well substantiated. Every conclusion or recommendation can be traced back directly to the specific data points and the explicit principles, the rules that were used to reach it.
Okay, so how does it actually work? What are the components?
Well, at the very core, there's a knowledge base. This isn't just a standard database. It's designed to store all the relevant data plus the decision-making principles, the actual rules and logic the investment team uses.
Got it. Data and rules together.
Right. Getting data in is handled by fairly standard data pipelines, but the really unique part is the knowledge pipelines.
And that's where the human experts come in, making their knowledge explicit.
Precisely. This is the frankly difficult process where the human investment experts sit down, analyze their own decision-making, debate it, refine it, and then codify that complex, often implicit knowledge into explicit rules or principles that can be put into the system. The sources emphasize this is a significant effort requiring a lot of discussion.
I can imagine. It's hard to explain exactly how you know something sometimes.
It really is. Then a calculation engine takes these codified principles and applies them to the data currently in the knowledge base to generate analyses, forecasts, or recommendations. And finally, interaction tools, dashboards, reports, visualizations are crucial for the human team to feed information into Samuel, understand its outputs, and basically collaborate with their digital colleague.
And how does APG use it day to day?
It supports their whole top-down investment process. So from deciding which regions look attractive, down to which specific sectors within those regions, and finally evaluating individual investment opportunities. Samuel takes inputs, runs its models based on the stored principles, provides baseline views, and can even challenge the team's assumptions if a proposed investment doesn't align with the codified logic.
Can you give an example of one of these principles in action?
Yeah, the sources use the example of calculating rental growth for an office building. Samuel might have a principle stating that rental growth depends, in part, on the quality of the building.
Okay.
But building quality isn't just a simple number. It's determined by other principles, which might look at factors like, say, employment growth in the building city, its sustainability rating, like an energy label, maybe how constrained the supply of similar buildings is in that specific area.
Right.
All these factors are linked together through explicit rules.
So it's like a tree of dependencies, breaking down a high-level concept like rental growth potential into its constituent parts based on defined logic. How is the knowledge base structured to handle these complex relationships and allow for that transparency?
It uses a graph database. The core idea is storing information as simple statements called triples: subject, predicate, object.
Yeah.
For example, building 1, subject, is located in predicate relationship, Amsterdam, object. The system has an ontology, which defines all the valid types of things and relationships, predicates, and then the knowledge base is filled with instances, millions of these specific factual triples.
And this structure lets it make connections, infer things.
Exactly, because the relationships are explicit. If the graph knows building 1 is located in Amsterdam, and it also knows Amsterdam is located in Europe, it can automatically infer that building 1 is located in Europe without being told explicitly. The sources show a more complex example, Exhibit 3, where multiple pieces of information, maybe the building's entry yield, its energy label, sector data like employment growth, which itself might be calculated via other rules, all combine, based on defined principles, to infer a higher-level concept like whether the property is an attractive investment.
And because it's all linked triples, you can literally follow the chain of reasoning back through the graph, see exactly which facts and which rules led to that attractive conclusion.
That's the key benefit. That traceability, that transparency is absolutely essential when humans are making multi-million-dollar decisions based partly on the system's output. They need to understand and trust the why.
Okay, that makes perfect sense. So let's try and tie all these threads together now. We've covered a lot of ground. We started with reinforcement learning, Q learning, this idea of agents learning optimal strategies through interaction, through trial and error, getting feedback.
Learning by doing and figuring out that tricky delayed reward problem, balancing exploration and exploitation.
Then we saw how that kind of AI and complex simulations really need accelerated computing GPUs to handle the sheer scale and complexity of data in finance today, making it possible to build bigger models, analyze more data, and iterate way faster.
Absolutely. Accelerating everything from data prep to training, inference, simulation, and even explaining the AI's decisions.
And we looked at specific applications where this accelerated data-driven AI is being used, pulling ESG insights from massive amounts of text using NLP, analyzing satellite images for spatial finance, using simulation and ML to build more robust investment portfolios.
Right, tackling real-world problems with diverse data types.
But then we also explored a fundamentally different approach, symbolic AI. Not about learning patterns from raw data, but about explicitly encoding human knowledge and rules to ensure transparency and leverage expert judgment, like in the Samuel system at APG.
Exactly, showing that AI in finance isn't monolithic. It's a toolkit with different approaches suited for different needs. Sometimes you need pattern recognition from data, sometimes you need explicit auditable reasoning.
So the big takeaway from these sources seems to be that AI in investment is really this diverse collection of techniques. It's not just one thing. And powerful computing is the engine making many of these advanced applications feasible, allowing firms to tailor these tools to extract specific insights from all sorts of data text, images, market data, even codified human expertise to support really complex financial decisions.
Yeah, that sums it up well. And for you listening in, hopefully this deep dive has given you a much clearer picture of the concepts driving these changes. You've seen how different kinds of information are being turned into actionable insights, how machines can learn in different ways, and how computation enables it all. You're better equipped now to understand the AI landscape in finance, see where these tools fit, and appreciate how they're helping cut through complexity to potentially find an edge or manage risk better.
It's definitely been illuminating unpacking all of this. Thanks for walking us through it.
My pleasure. It's fascinating stuff.
So a final thought to leave you with. Given all these different ways AI is being used, learning from interaction, processing vast data, applying explicit rules, and how they're often supercharged by computing, where else could these approaches, maybe combined in new composite ways, unlock completely new levels of understanding or performance in finance that maybe we haven't even thought of yet?
That's a great question. Definitely something worth pondering as this field keeps racing forward.
Indeed it is. Until next time on The Deep Dive.